Hello, welcome to this little session on chi-square testing with geometric distributions. I've put together a little example here which is a very similar structure to the example on the Dr. Frost PowerPoint, so this will supplement that. It's just another look really. This one's about Reginald, who is an esteemed musician. Every day plays a musical piece on his saxophone, a very complicated one to challenge himself. He continues to play the piece until he makes zero mistakes, so he keeps trying and trying. If he makes a mistake, he starts again. Reginald thinks there is about a 60% chance he will complete the piece with no errors. Over the course of 200 days, Reginald records how many times he starts the piece. The results are recorded in the frequency table below. So the number of starts, we've got 115 times. He only needs one. He gets it the first time. 2 starts. So he makes a mistake and then he has to do it again. But on the second attempt he does it. That's 50 times. He messes it up twice. So he makes 2 mistakes. So he needs 3 attempts to get it right, 25. And then 4. 4 attempts, 10. He never needs more than 4 attempts. Hope that's clear. So 115 times, he nails it first time. So here are the questions. Calculate the expected frequency if the number of attempts is modelled as a geometric distribution with parameter 0.6. So probability 0.6. Formulate the null and alternative hypotheses. Is Reginald right in his assumption? Test at the 5% significance level. So if it's 0.6, so we're assuming it's going to be 0.6 each time's independent. So we'll see how that works now. Here we are, here's the answer to A. I've just printed it, I've just typed this out this time rather than writing on here. So the number of starts, I've made a group that's 4 or above, just as convention is. There's the observed frequencies. There's the probabilities. Understand the geometric distribution, so that would be 0.6 to get it on the first. To have it on the second start, so the number of starts 2 required would be 0.4 times 0.6, so 1 failure times 1 success. If I need 3 starts, it would be 0.4 times 0.4 times 0.6. And then this, because it's 4 or above, we need all of these to add up to 1. That's 0.064. So we're just working out the probability of needing 1 start, 0.6, because he gets it right 60% of the time. This one of 40% times 60%. This one 40% times 40% times 60%. Well, based on that, these are our expected frequencies. How many times should he need 1 start? Well, 60% of 200 is 120. Here, 24% of 200 is 48. And we can see here our expected frequencies. So we need to complete this table here. I've set this up in advance, so I'm just not writing it as I would do normally on these videos. But I just want you to see clearly where everything comes from. There's the number of starts he needs, and he goes up to 4. So we call that 4 or above just to be complete, because anything, any number, any integer is possible. It could be 100, but that doesn't actually happen in this case. These are the observed frequencies, what actually happens. This is the probability of 1, the probability of 2 starts, 3 starts, 4 starts. And this is the expected amounts based on the probabilities. Okay, this is quite an important bit. We need to formulate the null and alternative hypotheses. This would be part of any hypothesis test, so we should always write them. The null hypothesis is X is such that it's a geometric distribution. It's a random variable that is geometrically distributed with a parameter of 0.6. So we say that is a suitable model. The null hypothesis is that is a suitable model. And the alternative hypothesis is that X is such that it's geometrically distributed with a parameter of 0.6 is not a suitable model. So we're going to be really clear when you're writing those. Okay, finally, we're going to do the hypothesis test. We're going to test whether Reginald is right in his assumption at a 5% significance level. Put the table on because it's relevant. Here it is. Here's our goodness of fit calculation. Just remember where we get those from. The 5 squared over 120. Well, the 5 is the difference between the expected amount and the observed frequency. We square it. So it doesn't matter about the sign. It doesn't matter whether it's negative or positive. So 5 squared over 120. The denominator there is the expected amount. So 5 squared from the difference over 120, which was the expected amount for one try. The difference between observed and expected in 2 is 2. So 2 squared over 48, 48 being the expected amount. 25 and 19.2 have a difference of 5.8. So 5.8 squared over 19.2. Hopefully you're getting the idea. All we're doing is putting those numbers into a calculator. 12.8 minus 10. 2.8, so 2.8 squared over 12.8. We add all that together and we get a nice small number of 2.65625. That's small, that looks small because the difference between the observed and expected is relatively small. They're relatively close, which tells us immediately, okay, it's not going to be a bad fit, but is it good enough according to the critical value? We've got here the degrees of freedom is 3. Well, we've got 4 columns, 1 takeaway, 4 takeaway, 1 is 3. That's why that works. We haven't calculated any statistics in this. We've just given an assumption of 0.6, so it's 3. The critical value, we can look this up in the table. Chi-squared of, with degrees of freedom 3, at 5% significance level is 7.815. Now, you need to write this. 2.65625 is less than 7.815. So our test statistic here is smaller than the critical value. The goodness of fit is smaller than the chi-squared critical value. That means it's a pretty good fit. Means there's not much difference, not a significant amount of difference between observed frequencies and what we should expect given the model. So we write this, we write insufficient evidence to reject the null hypothesis. We can model the number of tries by a geometric random variable with probability of 0.6. Okay, thank you very much. Hope that's clear. Bye.